Cohesion and adhesion. Cohesion is an H bonding between H2O molecules. An example of this is water gliders that look like they are quote-unquote walking on the water. That is an example of surface tension. Surface tension is basically when the water is quote-unquote sticky and things can move on top of them. That's when a water has an H bond with another water. Adhesion is H bonding between H2O and other substances. Capillary action is the movement of water within the space of a porous material. An example of this is when a cloth is placed in 2 cups of dyed water and the dyed water slowly moves up the cloths. That is an example of water with an H bond with another substance.
So we're going to be talking about the high heat evaporization water property. Basically 3 things: the sweat, hydrogen bonds, and then boiling and evaporation. First, we have sweat. On a very hot day, you are outside, you're practicing, and the sun is beating down on you. You get super hot, and your body feels so hot. And your body's way of cooling down is actually to sweat out all of those toxins, and it's actually going to cool you down, and that's your body's way of evaporating all of the sweat that's locked in your pores and your sweat glands and stuff like that. But those who can't sweat become very unhappy people because they get rashes all around their body where their glands are not allowing them to release that vaporization from the sun and that their sweat glands have released. But for boiling and evaporization, boiling is going to be caused from a direct heat source. And the bubbles from boiling, just let me draw my little boiling. The bubbles that are created when you boil are actually going to form and rise because of the vapor pressure that can overcome the atmospheric pressure. And evaporization doesn't get those bubbles because the vapor pressure doesn't overcome the atmosphere pressure. So an example of vaporization is the sun beating down on the ocean. The sun beating down on the ocean or any body of water, and you have that warm surface. It's like a little bit warmer than the rest. That is sooner or later going to evaporate because this right here cannot overcome the atmosphere pressure. But considering you have a direct heat source for your boiling, direct heat source, this is a heat stove or one of those little things, the bubbles are going to rise, form, and then it's going to boil and create steam, which is another form of water in a gaseous state. The hydrogen bonds, now this is where we get into the hydrogen bonds, have to have a high enough heat. This is where the heat is super important. They have to have high enough heat for them to break. They can't break unless they have a force upon them to be broken. And water cannot evaporate unless the hydrogen bonds break. So, the sun that beats down around this little hydrogen beaker, yes, it can't form bubbles, but it can still evaporate because the sun is creating an overall heat source around this beaker. If you keep it in like a little greenhouse, that's even better. But if you keep it in a freezer or a fridge, the water is just going to stay the same height. It's not going to evaporate, and it's not going to boil because there's no heat, there's no sun, and there's no heat putting a force on it. So it's just going to stay like this, and then that is not an example of high heat evaporation. This example is for the solvent of life. So I currently have like a definition that I've kind of came up with, that the solvent is basically a substance that has an ability to dissolve a solute, and a solute could be one of these two things right here, the salt and sugar. So we can start off with the sugar. So when you have a coffee and you have that clump of sugar in the bottom, that eventually goes away because the sugar has actually dissolved into the coffee, creating a different substance or a different kind of like liquid or solvent. And so the coffee, has the ability to dissolve the solute, which in this case would be the sugar, which then leaves it with none. And it's now in as a whole little thingy. And now all the sugar's like in there with the coffee. But for salt, say you're boiling a pot of water and you want to put pasta in it after, a lot of people would put salt in it. And everyone's like, oh my goodness, the salt is going to be so salty. Well, the salt is actually going to dissolve into the water, allowing one, the pasta not to stick. There's a little cooking note for you. And then two, the water is going to have a different effect. So let me grab a different color here. Instead of it just being regular water, not salty, it's actually going to be salt water, almost like the sea, but not as salty. Because the salt is going to go from just sitting on the bottom to actually boiling up into here. And it actually, you don't even have to boil it. You can just have a plain thing of water with salt at the bottom. And then after long periods of time, it's going to go from that to a nice salty substance. And then just one more little example here is actually going to be this. Just give me 1 second. So this is a picture of M&Ms. Oops. Of M&Ms that are dissolving into the water. Like the outside is actually the part that is a solute. The whole M&M or Skittle is a solute, but it's going to take the color, become a lighter shade, and change whatever solvent it is in and turn it into that color, as you can see in this picture. So, for example, if I were to draw this out, I would have my bowl of water, if I could move this.
So one of the properties of water is the lower density as a solid than as a liquid. So basically what happens is when water itself freezes or becomes a solid, the hydrogen bonds form into a crystal and they push out further, creating a lighter surface on top of the liquid. So it actually ends up being lighter than the water itself. So that's why you'll see a layer of ice on top of a pond during the winter rather than all of the ice just sinking to the bottom, and then the whole thing would just freeze. So you see here, when I put my ice cube in my cup, it floats to the top. And no matter how many ice cubes I throw in there, they all float because the density of all of them is very similar because the hydrogen bonds themselves are what makes it lighter than the liquid. Another property of water is the specific heat property. So what happens is, to change the temperature of water, a lot of energy is needed to have the molecules move faster or slower because the speed of the molecules determines the temperature of the water. The faster it is, the warmer it is. The slower it is, the cooler it is. And so right here I have a cup of tea that is steaming, obviously, and it's registering in at 136 degrees. And I have an ice cube here that's a little frozen, and it's registering in at 58 degrees, which probably isn't right, but it's close enough. And so what I'm going to do is I'm going to put the ice cube in my hot cup of tea, and I will be right back and tell you the temperature in 2 minutes. Okay, so I added 2 more ice cubes to my tea, and so I now have 3 ice cubes in about 8 ounces of water, and let's see what the temperature has gone down to. So now I'm still only at 101, and I was going to go down to 80, but I've already put 3 ice cubes in, and so that just kind of proves how much energy is really needed to cool down the water temperature. Okay, another example of this specific heat property of water is when you're heating up cold water. So right here I have a cup of ice water, and I have some hot water that I used for my tea earlier. And the temperature of my ice water right now is only about 73 because this is my second take. And then in the kettle it's 149. So when I add my warm water to my cold water without breaking my glass, and then I wait about 5 or so seconds, it's 78. So as you can see, it takes a lot of energy to change the temperature of water because it doesn't happen right away. It takes time because that energy is needed.